How's your audio?
Testing. Yeah, it's all good. Okay, thanks, Jared. Yeah, thanks to everyone for who's been involved in organizing this and for inviting me. I normally work on star formation, erupting young stellar objects, occasionally on brown dwarfs. I'm going to talk about giants. So if you know about giant stars, I would love to talk to you afterwards and you can explain my data to me because this is something unexpected that we've discovered. Essentially, it's a good old-fashioned, stellar astrophysics mystery. And I'll just show you the data and maybe as a group, you guys will have better ideas than I do as to what it's all about. And in fact, my student, Harry Haranmuthu, who's mostly working on YSOs with me, but has produced some of the more recent data for this. Okay, what I'm going to present is starting off really with just the two papers we published at the start of the year when I did a search for all this infrared variable stars in the VVV survey that varied the most. So it's about 200 stars that varied by more than 4 magnitudes of all types. So erupting YSOs, novae, anything else, weird things. We published those, and then I'll follow on with some more recent data that we've dug into the data a bit further. This is just a nice, pretty picture to show you what one of these looks like from the press release. So essentially, we have very crowded fields near the center of the Milky Way. This is the nuclear stellar disk of the Milky Way. It's basically the same place as the central molecular zone, though it's not really understood how the central molecular zone relates to the nuclear stellar disk. They just both happen to be in the same place. Diameter of about 3 degrees on the sky, a small fraction of the degree in scale height. And the stellar density there is orders of magnitude higher than the rest of the galactic bulge. So here you see a star. There's one of these dipping giants. Now you see it, now you don't, and it starts to come back again several years later. You can notice it's fainter and redder as it comes back there. Data comes, as I say, from the VVV survey. That's VISTA variables in the Via Lactea, so obligatory picture of the telescope at Paranal. VIRCAM has now been taken off and is being replaced by the foremost spectrograph, so we won't be getting more photometry out of that, unfortunately. This is the footprint of VVV itself. So the VVV survey ran for about 10 years, from 2010 to 2019. We have a little bit of data post-COVID, but not much. And we did this light blue region is the bit we've been analyzing. The VVVX extension is about 3 times the size. Both of those came to an end in early 2022. So we have on the order of 10 to the 9 light curves. Earlier papers published and shown in dark blue there. The data release with the light blue area, 500 million light curves. We're submitting the paper next week. So that will all be public shortly. If you want something in the meantime, do just come and ask me. And hopefully in a year or two after that, we'll have the rest of the red area, which is being processed at the moment with PSF photometry. Okay, so as to come on to the actual discovery, in the paper, as I say, I found it was actually 222 stars that varied by more than 4 magnitudes. And it's a bit of a jumble trying to classify things and say what they are. So I broke things down into all the different categories and then somewhat belatedly plotted where they were in galactic coordinates. And I've stretched the vertical scale there. As you can see, there's plenty of CVs and YSOs. But there was this funny group of dipping sources which are very strongly clustered near the center of the galaxy. And I was actually quite late in the paper that I made that plot, because I'd noticed there was a bit of a cluster of what might be erupting YSOs or might be dipping YSOs. We weren't sure what they were, but it wasn't until we actually got some spectra of a few of these and realized that they were giant stars rather than YSOs going through a dip, that I went back and realized, oh, I should plot where all the different types of things are, not just the YSOs. And this basically stood out in a big way. So if you just plot everything in the kind of bulge region, you can see it's a mess. So it did take a bit of work to do this. And as you can see, zooming in close, it really is kind of a flat disk-like structure. That's pretty much where the nuclear stellar disk is in the Milky Way. Okay, in terms of properties, well, this is what these dips look like. I'll get that to come up. So here are the first 12 of them. You can see the light curves are all different to each other. So these are asymmetric dips. There's no obvious sign that they are periodic. In some cases, we weren't sure. I thought that might be an erupting young star, FU Orionis outburst, but spectra show otherwise. Some cases, very obviously a classic dip and recovery, but I thought it might be a YSO. I think I presented that at a conference a while back as a dipping YSO, where it's a part of a YSO disk causing the dip. It's not, it's a giant star. They're all different to each other, but common characteristics is that these dips last at least 6 months, maybe several years, They are, in nearly all cases, they're bright in TUMAS or UKIDS data taken some years earlier. So even in the ambiguous cases, we're pretty sure that we're looking at a dip and not a YSL outburst. Most of these are asymmetric, so we don't think it's just a very well-defined circumsecondary disk around a companion star, which happens to be going in front of the line of sight and blocking out all the light from a giant star. That sort of thing does happen. Epsilon Aurigae is the most famous case, where every 27 years, a companion object with a disk around it passes in front of this giant star and the light dips by a factor of 2. We discovered one a few years ago in VVV, we called VVV WIT08. Lee Smith wrote that up. We have a giant star that dips by 4 magnitudes with a perfectly symmetric V-shaped light curve. You know when you're seeing a disk occulting a giant star. In these cases, it's not quite so symmetric, but nonetheless, there might be some ways that a disk can give you an asymmetric disk, an asymmetric dip. Here's another 9 of these, just to give you a bit more variety. You can see that there's usually some variability outside of the main dip, and it is indeed generally quite asymmetric. The recoveries are sometimes quite sharp, which is interesting, varies though. Here are the spectra. So we got spectra of 7 of these to see if they were YSOs or giants or something else. They all look more or less the same. Fitted temperatures between 3100 and 4100 Kelvin. So we're looking at late K or early M-type giants. There's no sign of carbon-rich features like C2. So we think these are O-rich stars. And we were able to estimate the temperature and the metallicity by using a method that was developed by Fritz et al. 2021. They're just looking at CO and sodium-1 in these X-shooter spectra from the VLT. So I wouldn't take the metallicities as being in any way, definite high-resolution spectroscopy results. This is relatively low-resolution R of 8000 spectroscopy with X-shooter using a very simple method. But nonetheless, using this method, which was calibrated off better understood stars in the paper by Fritz et al., we got supersolar metallicity in 6 out of 7 cases, and that was a nice finding because I was suspecting that the clustering that we're seeing in the nuclear disk might relate to the fact that the nuclear disk is known to be a region of high metallicity, a region where there's a lot of stars of supersolar metallicity. So I said to my postdoc, Jen, can you please try and calculate the metallicity for these things? And they did come out, in most cases, as above solar metallicity, as far as we can tell. If you compare these spectra, if you take these very red spectra and de-redden them by 5 infrared magnitudes, that's about 50 optical magnitudes of extinction, then they look enormously like a standard that I've took out of the X-shooter spectral library. There's really very little difference. There is not much sign in that spectrum of any circumstellar dust. You can just de-redden it and it looks like a normal star, essentially. If you look at the near-infrared colors, we only have about 2 or 3 epochs of color variability data, but these changes for the individual stars going from blue to red, each connected pair of points is 1 star. They seem to roughly follow the reddening vector. So we think this is extinction by submicron grains. If you look at them in Spitzer, fortunately, most of them were detected by Spitzer in the GLIMPS-2 survey in 3.6 and 4.5 microns. Well, there are about 5 of these where the colors are red enough that I think we are seeing emission from circumstellar matter there, warm circumstellar dust. The rest of these, although they're quite red, the extinction is so high in this part of the galaxy, and these stars in particular have such high extinction that these fairly red colors could just be explained by extinction. So only a minority of these are showing such red colors that we can be pretty confident that there actually is emission from warm dust there. If you look at the 4.5 minus 8.0 micron color, I've deliberately left a big gap here on the right where the redder stars in the galaxy, some of the redder YSOs tend to be, just to show that none of these are super red in the 4.5 minus 8.0 micron color. So none of these would show up in Thomas Robert Hale's list of the reddest stars in Spitzer. Okay, this is a plot of the metallicity distribution in the nuclear disk from Fritz et al. Lots of people have had their own versions of this. People tend to think it's supersolar. In this plot, it's only mildly supersolar, but this is just to underline the fact that there are a number of stars here which are above solar metallicity. We don't really know what the metallicity distribution of the nuclear stellar disk actually is. The whole region is hard to see and not very well understood, and we weren't really sure it even existed until sort of the early years of this century. So it's kind of just understanding what the nuclear stellar disk is and what its properties are and where it comes from is something that's kind of new. Jason Sanders tells me that most of the stars there are a few billion years old. We're trying to get a handle on the dynamics. There was a VVV paper work by Matthias Sormani where he was able to use the VVV proper motions and radial velocities, which came from an earlier survey with the VLT, actually the Fritz survey, to try and work out the dynamics of the nuclear stellar disk, and you can indeed model this quite well. But we don't, as I say, understand what the relationship between the nuclear stellar disk is, or how it comes to be, and the age distribution of all the stars there. It's an area of active research. Okay. Now, this is the bit where I might suspect that a few people in the audience who work on giant stars might have seen a few things like this before. I'm not sure. If you have, come tell me afterwards. There have been a couple of earlier papers where people have seen similar things at lower amplitude. There was a paper a couple of years ago by the VVV team, which I was on, which showed a few stars with smaller dips. And at the time, we didn't realize this might be a bigger deal, and that these dips were very concentrated only in the center of the galaxy kind of region. But we think what we might be seeing is a dust puff along the line of sight. So something similar to the R-core Bohr phenomenon that you get in G-type supergiants, or to Betelgeuse. Another possibility is that, so another early observation was by Whitelock. I'll skip over that, but was carbon stars in nearby space. So the two main interpretations here, just to summarize what I've said, we might be seeing a dust puff origin where you have a blob of material which is created, essentially mass loss in evolved stars is radiatively driven, but it's assisted by convection and pulsations and shocks. So it's a complicated three-dimensional process that can lead to ejections of a blob of dust along the line of sight rather than a more uniform spherical shell. We know there isn't a big uniform spherical shell here because these stars are not red enough in the Spitzer data. The other possibility, though, is that we're actually seeing circumstellar matter from a circumsecondary disk. Can't rule that out. Matt Kenworthy tells me that tilted disks could potentially produce some of those light curves. We shall have to wait and see. There is known to be a phenomenon of matter distributed around the orbit of a companion, though. If you have a companion which doesn't have a disk, but there is matter sharing the orbit of that companion, that is one of the theories that's thought to be responsible for long secondary periods, which are seen in some Maya variables. They tend to have shorter periods than what we're seeing, but nonetheless, that is a valid alternative explanation of the data, is that you've got a companion star and there's matter in the orbit of that body. This is just to quickly flash up, since I'm low on time. This is what we've been doing just lately. I went through the data that Harry Harran, my student, had picked out, looking for YSOs, everything that varied by only 2 magnitudes rather than 4 magnitudes. And we've now up to about 160 or so of these dipping giant candidates. We don't have spectra for most of these yet, but you can see they're tracing out the structure of the stellar disk, nuclear disk of the Milky Way, but there is some spread into the inner bulge as well, which is also generally a metal-rich region. And there's also a connection, really. If you look closely at this, you'll see that it's not really centered upon longitude 0. It's shifted slightly to about longitude plus 0.5 degrees, that distribution. And that is also true for the central molecular zone. The CO gas distribution is slightly offset to positive longitudes, and so is the dust emission as seen by Heigl at 500 microns. Okay. Probably don't have time to say this, but just there are some funny things going on in the same region with the Mira variables as well. So if you look at the pulsating stars in our sample, we only had 2 or 3 that were projected in the nuclear disk. You do get some cases where there are stars with very small Mira-like pulsations, but about 3.5 mag dips. And these dips as great as that only happened for the 2 or 3 stars that would happen to be projected in front of the nuclear disk. So maybe that whatever's happening with these giant stars is also affecting the pulsating stars as well. Okay, and I'll leave you there with my summary. We have quite a long wish list of more observations that we would like to have, but if anyone has any ideas about what we're seeing, please come and let me know.
Got a question right here. Glasses.
Hi, Zach with State. I live mainly in the dwarf land. It's a question, but I was wondering if this is material coming off from the surface of the star, does this have implications for feedback processing?
Yeah, I mean, that's a really good question. I mean, this is the kind of bit where you want to write a spiel to funding committees and telescope committees as to why is this important, and so. Yeah, we don't know how much matter is being thrown off because we can't directly see the warm emission from that, except possibly in a handful of cases, as I mentioned. So because we don't have an idea of the spatial scale of whatever these dust puffs are and how much matter is being thrown back into the interstellar medium, we can't say yet whether it's important or not. But if it is linked to supersolar metallicity, and that's the reason why we're only seeing it in this one special part of the Milky Way where the metallicity is high, then you might think, well, obviously this could matter for the feedback in the central molecular zone, but it could then also matter for starburst galaxies and other places in the universe where the metallicity is higher than it usually is in the Milky Way. Your guess is as good as mine.
Here. Give us your name.
This is Laura Vega. I was curious if you have AABSO light curves for these targets and if any of these are binders.
Okay, good question. Yeah, maybe should have made a bit clearer that the reason probably this hasn't been seen before is that we're doing this in the infrared at 2 microns. And so there's about 50 magnitudes of extinction hiding most of these things. So you really couldn't do this before VVV. I think people would have noticed these a long time ago if you could see them in visible light. That said, those new ones I discovered, the 160 odd objects, there's a couple of those which are in Gaia. I don't yet know if they're the same kind of thing. There might be a few examples which are conveniently closer to us, and we could then go and look for the AABSO light curves. Gaia light curve for one of them looks quite similar to the VVV light curve, actually. So we shall have to wait and see.
Last question. And get our next speaker up in the meantime.
These objects are in a region of the magnetic sea, which extinction, gas extinction.
Yeah.
Consider the possibility of material or line of sight. Clumps of stellar dust.
Yeah, no, that's a good question, which have been asked before. So the best argument against it, well, one argument is just that the timescales are quite fast for large interstellar gas clouds to be moving around on a time and changing things on a time scale of a year or two. But the bigger argument, I think, which I probably should have said already, is that I think these are asymptotic giant branch stars, if I didn't say that already. They're in about the right place on the HR diagram. So, but essentially, if you correct for all that enormous extinction, then the absolute magnitudes you get are about -6 to -8. So that if this was random interstellar dust clumps, of which there may exist in the central molecular zone, because there's a lot of structure there, you would expect them on average to be occulting completely boring red clump giant stars with an absolute magnitude of -1.5, not these somewhat overluminous AGB-like stars. So that's kind of my answer to that one.
Thank you.
Me?
Try that again.
Hello, can people in the back hear me? All right,
Yes.
great.
All right, our final talk of this session is going to be Lucy Liu from AM